Hello and welcome to the AI for Good webinar series. My name is Ida Deburi from the ITU and I am pleased to introduce today's webinar. ITU is the UN Specialized Agency for ICTs, and we're also the organizers of AI for Good in partnership with 40 UN sister agencies and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the Sustainable Development Goals and scale the solutions for global impact. We are pleased today to discuss AI model data integration for understanding climate impacts in the Earth system. We encourage you to ask questions in the Q&A box and say hello in the chat. You can find these at the bottom of your screen. So without further ado, I would like to welcome our moderator today, Professor Philip Steer and Duncan Watson-Paris from the University of Oxford. Over to you, Philip.
Thank you very much. So welcome everyone again for another AI for Good session. Today the focus will be really on understanding climate impacts, and I'm very much looking forward to that. So we have two fantastic speakers. We have Markus Reichstein from the Max Planck Institute for Biogeochemistry in Jena and Michael Obersteiner from the Environmental Change Institute in Oxford. But we will kick off with a talk by Markus Reichstein. And so we'll introduce Markus first. So Markus has a background in ecology, landscape ecology, and then did graduate studies, worked on drought effects on ecosystems. As a Marie Curie fellow, he went to Italy, and then he joined the Max Planck Institute for Biogeochemistry, first as a group leader, but then also since 2014 as one of the managing directors. He's also co-director of the Michael Stifel Center in Jena for data-driven and simulation science, so very much to the theme of this session. But today he'll speak, as I said, around AI model data integration for understanding climate impacts. And I just hand over to you, Markus.
Yes, thank you for the kind introduction, actually the invitation to have the chance to talk about our work here in this fantastic seminar series. I'm sharing my screen now and hope you can see it. Yeah, I want to talk a bit about exactly that topic, understanding climate impact in the Earth system and the role AI and model data integration can play for this. If you have listened to previous presentations, then the next slide is probably not a big surprise for you. It's about the Earth system, and the Earth system is so exciting scientifically because it's a complex system where biological, chemical, and physical processes come together to form the system. And scientifically, it's also very challenging because it's a unique system. So we have to base our knowledge largely based on observations, and we cannot do like multiple experiments with a set of multiple Earths like we can do in other fields of science where we can execute these experiments. You see also on the right-hand side, really the challenge is also this multi-scale property where basically from molecule to globe, we are bridging 17 orders of magnitude in space, and we have similar scale issues if you think about the time dimension. Usually this complex system is divided conceptually into spheres. Very simplified picture, but it's important that we have these subsystems that interact with each other: the atmosphere, biosphere, cryosphere, and the hydrosphere. And of course, since at least 2,000 years ago, but of course with the Industrial Revolution even stronger, the humans, which make up the anthroposphere, which we can actually see now very clearly from space, for example, with the night lives. And these different system components basically form the system by interacting, by exchanging trace gases and energy, basically to then give the whole Earth system behavior. And this already is kind of conceptual model of the Earth, that is textbook knowledge if you want, but it shows already that we try to conceptualize the Earth as a system of subsystems, and that has been perfectionized actually by the Earth system modeling community. That has been a kind of really initiating a diagram from Bretherton. We don't need to go into detail, but the idea is basically of this system modeling to have a reductionistic model where the physical climate system, the biogeochemical cycles, both for land and for ocean, are modeled kind of from first principles. And then everything is put together with the idea, if these models, sub-models work together, we can get a good numerical model of the Earth system behavior. And that paradigm has been, of course, very, very successful. And with increasing computational power, one can do amazing things with that. I think you had also a talk related to this digital twin Earth, where we can really simulate the Earth's dynamics, the dynamics of the atmosphere now with high resolution, and it's hard to distinguish the modeled results from the observed results and dynamics. On the other hand, there has been also quite some setback and challenges that are still there, and that are particular in the climate sciences, and more particular even in the carbon cycle. Carbon cycle climate and dynamics, as you can see here. If you look into the future, we see here basically the evolution of how much carbon dioxide is taken up by the terrestrial ecosystems. You see that there's now a slight uptake of carbon dioxide. This is good. So basically, roughly 25% of our CO2 emissions are taken up by terrestrial ecosystems. So that mitigates a bit the greenhouse effect. But if we look into the future, we see that some models say that this will increase strongly, but other models say, well, no, by 2050, and then later, this current uptake of CO2 will be actually reversed into a source of carbon dioxide, which would then exert a positive feedback and put additional CO2 into the atmosphere and will enhance the greenhouse effect. So the kind of these feedbacks are very uncertain and cannot be resolved simply with this reductionistic approach. Obviously, several models come up then with different predictions. And this is a publication from 2014, but it actually has been already found 2006 by the same author. And I think one can say actually that this picture, but also other ones about cloud feedbacks, for example, have really led to a crisis in the Earth system science community, because it shows basically that our knowledge seems to be still limited about this complex system. And that actually has led us in 2019 or before actually think about how the situation can be improved. And one of the conclusions that we had is that really the integration of the richness of observations with intelligent systems needs to be improved, and we need to kind of bring together advances in machine learning, deep learning, and together with this process understanding that is embedded in the Earth system models. Basically, the starting point is really that, and that is also for the machine learning people, that Earth system data is really prototypical for big data, with all the 4Vs very prominent with Earth system data. But one thing that I think is really unique and also challenging is a variety of Earth system data that we have, that you can see also in the middle. Partly we have point data, time series observation at individual points. Then we have with the Earth observation, with the remote sensing, we have global observations, spatially dense grids. And then we have integrated variables like catchment observations in watersheds, or also airborne campaigns that also usually have a kind of an airshed where they take the observations from. So quite diverse data. And the challenge is, of course, to bring that data together and generate knowledge from the data. I give you now one example where one can see that this variety of data can be also used in a synergistic way. It's work from our group very quickly. And one is basically trying to understand how ecosystems respond to climate variability and climate change. You see here a network of observations which observe in a non-destructive way the carbon dioxide flux from the atmosphere into the ecosystems, but also water flux, evapotranspiration from the ecosystems back to the atmosphere, and also energy fluxes. And these individual stations give really highly resolved observations that we can see here in these fingerprints, how we call them, or classically we would call them isoplete diagrams, where we have here the time of the day. On the x-axis and the y-axis time of the year, and then the colors code basically how much carbon dioxide is taken up. Green means it's uptake, red means there's release. We see in a tropical rainforest a typical pattern, year-round uptake of carbon dioxide when the sun is shining during the day, but a release of carbon dioxide when it's night. In a European beech forest, it looks different. In winter, the system is pretty inactive, but rather respiring. There are no leaves. And then rapid onset of activity in spring. And then in autumn, when the leaves are gone, everything stops more or less again. But you see that the rates themselves, they are as high as in the tropical forest, but they are just not operating year-round. And if we go into the Mediterranean forest, like here on the right-hand side, you can see that there's potentially also year-round activity, but then we have in summer here this depression of activity, and that is caused in this case not because it's too cold, but by drought and water scarcity. This is just an example. There's a lot of information there, but of course it doesn't cover the whole globe. So how do we go from there to get a global picture? It's too sparse just to do some statistical interpolation or so. And so the idea is basically that we use the variety of Earth observations. If we look here into this space-time diagram, these observations that I just talked about cover kind of 1 square kilometer roughly, and as long as they're running, so now for a couple of decades. But it doesn't go into the global scale, and that's where remote sensing Earth observation comes into play. That gives basically daily observations of the whole globe, but not of the quantities exactly that we that we want to look at, like photosynthesis or evapotranspiration, because these are functions that are not directly observable, but rather with remote sensing we only get the reflectances, for example. So the idea is to bring these two observations together at this intersection of the scales. Build a machine learning based model where the targets are predicted from the predictors. Can be a tree-based, method kernel-based, or neural network-based. And then once this model is established, one can use these remote sensing and meteorological data together to then do global predictions. With that, I mean, that was basically like 10, 15 years ago. We have been actually able to generate the kind of the first observation and AI-based maps, dynamic maps of the breathing of the atmosphere. Here we see the seasonal cycle, where we see basically the sink of carbon dioxide with the green colors, and when it really is, when it goes down. So this is kind of intuitively the sink of CO2 that the ecosystems provide. But of course, we go beyond those animations, and we can understand model behavior much better, or can constrain the models much better. For example, here, we see here in gray our estimates how the gross primary production, so how much carbon dioxide is taken up by the vegetation, varies across latitude. And we do have some uncertainty, observation uncertainty, but it's much smaller than the range of process models that were, for example, in the IPCC report. And so this can be and has been used to further constrain the process models and also better constrain than the carbon cycle climate feedback at the end. Another example that we can look at basically the radiation use efficiency of the ecosystem. So how much, with which efficiency is a radiation used to be converted into chemical energy? That is, first of all, the sugars and the starch in the leaves. This is used for bioenergy, of course, also, as you know. And if you look at that, it's the conversion efficiency is actually quite low. We see that just from the observational product, and it's particularly low if precipitation is limiting. So under dry conditions, it's even lower. Only the highest rates are basically achieved when precipitation is also high enough here, as you up here. But compared to, for example, photovoltaics, the efficiency is really very, very low. And I think that already shows that bioenergy is probably not the solution for our global energy problem or renewable energy problem that we have on Earth. I want to give you a second example where AI can help a lot. Is about detecting extreme events, detecting anomalies in the system. So we have, again, from remote sensing, we have these multivariate observations that we call data cubes, because we can arrange them in time and space as multivariate cubes. And then one can ask the question, when and where are these variables uncommon and strange and possibly with strong impacts? If we do that, we look in this space-time continuum. We can basically identify here with these blobs which are the situations in space and time where these variables have been abnormal in a multivariate way. And here's one very big space-time structure that we see here. It's in 2010, so you might imagine what has been detected here is a Russian heat wave, which had very, very strong impacts on health systems, but also on agriculture and last but not least also on the economy. Of course, this heat wave has been also detected before, but the thing is that we can basically detect these things with these anomaly detection methods without the assumption before, just from the data. And through this, we can then also detect other anomalies that have been maybe not so prominently seen, like, for example, the things that happen in Africa, just for example. And these are often hydrometeorological extremes. I want to make one point here about extreme events. It's really important to note that one can have the same weather, but different impact. And I think that's where this impact perspectives comes into play. We had just suffered from that truth in Germany last year, where you see on the left-hand side these big floods in Western Germany that caused this horrendous damage and ensured losses that were unprecedented. But if you just look at the climate or at the weather event with far more than 100 millimeters of rain falling within 24 hours, that was actually not so unprecedented. In the same year in April, it's less known, there was a very similar event in Eastern Germany in the Uckermark, indicated here on the right-hand side. And all the damage that was there was some streets that were a bit wet and maybe a couple of cellars, basements that were flooded, but nothing really serious. And why is that the case? This is because the ecosystems are different there. The geomorphology is different, with sandy soils in Eastern Germany and flat areas, while here in Western Germany, in the area, it was different soils and the kind of channeling systems. The geomorphology with this hilly terrain was very different, and that caused very different impact given the same weather event. I think that's really important. And we looked at that not for floods, but rather for drought events, or in general extreme hydrometeorological events here globally, with this database that we created with our anomaly detection method. And we also see here that in this case, the effect of these hydrometeorological extremes was not always negative. Quite often it was negative, here the red dots. But there are enough blue dots also where actually in this case, the vegetation activity was positively affected by this hydrometeorological extreme. And of course, that's a very important question, how to map extreme events onto the impacts. One can look at that in a bivariate plot here, for example, with temperature on the y-axis and surface moisture on the x-axis. But you see already that this doesn't really perfectly separate the positive in red, blue and the negative effects. Although one can say, yeah, with low soil moisture and high temperatures, it's probably more likely to have negative effects here. This cluster of red points, but it's not so clear. And that's again where machine learning and AI comes into play. In this case, we've been looking at a couple of predictors with an XGBoost algorithm and then explainable AI with a Lime method, which actually then also shows that the impact actually depends a lot on what land cover is there, with the forest being less affected, but it also depends, we see here, on the soil moisture during the event. If it has been high, then the effect is lower, but also the duration itself of the event was very important. So the longer the duration is, the more negative the impact of such an extreme event is. So we have to, again, consider several constellations and characteristics to understand what the impact has. So these were just two examples, one on the more regression type approach and for predicting fluxes, photosynthesis, and the other one more unsupervised detection of anomalies. But the limitations of all these approaches that I've shown so far is really that dynamic effects have been not really considered, or only considered with hand-designed features, because it was really a regression approach. Instantaneous remote sensing data and weather was mapped onto the ecosystem function that we wanted to look into. And dynamic effects can be modeled with temperature sums or with precipitation indices that also take into account past precipitation, but it's really hand-designed features. And secondly, the pixels were really pixel by pixel were kind of considered, so the spatial context was not really considered. And that's exactly where deep learning comes into play, because deep learning approaches exactly exploit spatial and temporal context. So again, we made that figure to show the machine learning community that there are so many analog tasks in the Earth system science that are already addressed with classical machine learning, like object classification goes directly into pattern classification of atmospheric rivers or cyclones or droughts. Super resolution maps directly to statistical downscaling and blending of climate models, for example, or weather predictions. This is more, if you want, on the spatial mapping. And then if we think about temporal dynamic systems, video prediction, which tries to predict how certain video scenes continue into the future, directly map onto short-term forecasting, for example, precipitation nowcasting, but also how vegetation behaves over a season or over several years. And last but not least, language translation, where a word really depends on, or the meaning of the word really depends on the context of what has been said 1 or 2 sentences before, is very similar to dynamic time series modeling, where we know that an ecosystem behaves very differently depending if 10 years ago there was a clear cut of a forest or not, or there has been another drought before where the system has been weakened, and so on and so forth. So this is really, really analog. I want to give you one example of this downscaling, which we thought very striking. Let's say, so we wondered if one can use AI for spatial prediction of impact at the landscape scale. So the idea is basically we have climate, of course, but also human and geo factors, and these together cause, if you want, or contribute to the development of landscape as we see them today. And the question is basically, if we have these factors, and often these factors are quite coarse scale, like weather information is on the several kilometer scale, as you can see, mean temperature, precipitation, cloud cover, then we have maybe some land use, some digital elevation model that's a bit highly resolved. But then we see the landscape now actually with the sentinels, we see them at 20-meter resolution. And the question is, can we basically conditional on those drivers? Can we downscale them, the drivers implicitly, and then also get the impacts? We did that with a deep learning architecture, conditional generative adversarial network. Some of you may know what that is. I don't want to go into detail. Can we predict this, how the landscape looks like, including the spatial features? And yes, indeed, it actually works pretty well. So here we see the targets on the one hand and then the predictions on the other hand. And I forgot now again which is the real one and which is a fake one generated with the AI. So the upper one is a predicted one. And you see that very different landscapes can be predicted or generated given those conditions. If it's cold or warm and so on and so forth. And even the spatial structures are very different. Of course, these are good examples, let's say, visually good examples, and one needs to look at that in a more objective way. What Chris Rekina actually also did, we looked at some landscape metrics here, like fractal dimensions or connectance. And what we do see is actually that this generative adversarial network, which considers spatial context, is always getting a better prediction of the landscape than, for example, a simple fully connected network, which is ignoring the space totally. It's no surprise, but also with compared to other approaches where basically the spatial information cannot be used because it has been permuted in space. So that has been quite nice to see that this works very well. And of course, it's tempting to use these models also for prediction, for saying, okay, now the landscape looks like this. And now let's use this model and see how would it look like if the temperature is increasing or if the precipitation is decreasing. It actually gives plausible results. If we have less precipitation, we have also less snow here. If it's getting warmer and drier, we get more dry landscapes. But of course, it's very dangerous because this is a really statistical extrapolation, what one should not do. And in this case, it is basically on the space for time assumption. So it learns basically how things might change in time from space. That's something that's being done in the geographical sciences all the time. Here it's perfectionized with an AI approach, but still the limitations are of course theirs. But one can at least use it to imagine how things can be. And one has always to consider other factors that might not be considered in such approach. But on the other hand, we do have, of course, also dynamic observations of impacts. A very nice example from the European Space Agency is the 2018-19 drought, where the landscape has basically changed from green to brown within a month, basically through this drought in Central Europe. And here it looks like, yeah, from green to brown. But if we actually look more local, then we can actually see that the impacts are locally much more differentiated. Here we talk about this very slide on carryover effects, memory effects for the subsequent years, but you see some red and some green. So it's quite some spatial structure. And why is that? That can be because north-facing and south-facing slopes are different. A hilltop might respond differently than a valley. Or if you are close to groundwater or to a river, then it might also have different effects. So these are all these spatial context effects that we need to consider if we think about and want to predict local impacts. Yeah, here's just another picture where you see that some trees die and others don't die with drone observations, and so we can get these much more differentiated picture. So that actually has led us, and there are people there out there. Actually, this is going to be also challenged in the Frontier Development Lab. Very hopefully, we have set up an EarthNet 2021 challenge to exactly address this problem of local prediction of climate impacts, where the spatial context plays a role and where it's not like a broad brush impact, but really locally differentiated. So we have basically these data cubes, and the idea is, given those climate core scale climate predictors, can we get to local impacts? So everyone is welcome. We have first approaches there, where the spatial context is kind of the spatial data is transformed into relevant features with a feature pyramid network, and then a recurrent neural network is used to predict the vegetation conditional on the weather impacts for kind of the next year with a daily time step. It looks quite promising, although it's certainly not perfect. So here we see how the targets kind of develop. Of course, we see the cut here of the cube, and here what the context recurrent neural network is predicting. There is certainly some similarity, but also you see too much smoothing here in the time series. So there's still some work to do, but it is at least promising, I would say. But of course, this is all, there's not much physical consistency, actually. That's really these black box approaches. And the question is, should we really throw away all the knowledge? And certainly not. And this is actually where the integration of knowledge into machine learning comes into play, which is very much actually the foundation of both our program with Gustavo Gonzalez in the Alice program on machine learning for Earth system science, but also in our recently founded Alice unit in Jena together with Joachim Denzler. You see here on the left-hand side exactly these different ways, or some different ways, how you can integrate knowledge. Already modeling something on a spatial temporal grid is some integration of knowledge. You accept some topology, for example. Then graphical modeling and causal modeling, where quantitative information about causal links can be integrated, is an important one. Jakob, I think Runge, who's a member in our Alice unit, I think he talked last week just about it. And I guess Gustavo mid-February will also touch that, so I will not talk too much about it. There are much more experts than I. I would talk a little bit about this hybrid modeling idea, which basically means bringing together really the machine learning approach with physical modeling in one system. So next slide should show that a bit from the system modeling perspective, where basically we have a system model consisting of submodels. The submodel is forced with some input. The output of that submodel is then the input to another submodel, and that can of course also feed back to the first submodel. So this is just a very abstract system model, and we were wondering about where actually machine learning can help to improve those models. Let me be a bit fast. There are 5 areas at least that we identified. Model emulation, I'll talk about it. One can drive a model with machine learning output from another model. This one here to avoid, for example, biases from the other submodel, to localize any analysis in a modular sense. The whole thing of model evaluation, model calibration, machine learning can help a lot. This is basically the analog to plotting scatter plots and calculating the RSP. Instead, doing that a little bit more smart and looking for patterns, separating noise and signal. But then really the idea of hybrid modeling is to replace the submodel completely with a machine learning approach, but integrate it in the system model, or also replace any parameterization that might be physically derived or just ad hoc derived with something that is more data informed. One could also call it hybrid modeling, but here we differentiate the two things. So the idea of hybrid modeling is also shown a bit here on the left-hand side. It shows that you get actually to more interpretability. The deep learning approach, where you have input, you derive simple features and then more and more abstract features by adding these layers. And the idea is that one of the last layers can be then actually physical model parameters that by definition are interpretable, and then they are put into the physical model to guarantee physical consistency, and then we get actually physical output that at the same time is maximally informed by the observations. There are some examples already in the literature. Maybe here on the right-hand side, I give you one example that is close to my heart. So the idea is, or the question is, how do we model transpiration from the vegetation into the atmosphere? And this transpiration is a water flux, water evaporation. It's a diffusion and an energy dependent process, so it's a very physical process, but how much can really evaporate also depends a lot on the stomata in the leaves, the pores in the leaves that open and close in a physiological, meaningful way. but there don't exist really very clear or unique theories about it, but rather competing theories, and everything is often formulated in a very empirical way. So what one could say is, well, we take the drivers from weather, put them into, for example, a recurrent neural network, and let the neural network sort out what is the best sequence of stormal aperture given the data, and then put this sequence of stormal aperture into this physical diffusion model as a diffusion constant basically, or coefficient, and to give then time series of transpiration and photosynthesis. That's a bit the idea. And this is kind of one perspective in this knowledge integration. Another one is more the theory-guided machine learning, where the cost function or architecture is guided by some theoretical knowledge. Kapatna and al. Have very nice papers on that. Want to give you, yeah, okay, it's time. 2 quick examples how that can work and what one can get out of it. One is a simple example of modeling respiration, where it's really more almost a toy example, but quite useful. So respiration can be modeled as a temperature function, an exponential function of temperature times a so-called base activity that depends on how many roots are in the system, how active are the animals and the microbes, and so on and so forth. And this equation basically already gives some confounding effects. So in some systems, the apparent temperature sensitivity looks like very strong, like in beech forest, because in summer, when it's warm, the system is anyway active. While in a Mediterranean forest, we get more this flat response, because in summer, when it's warm, it's also dry and the systems are not so active. So if you would just try to calculate here what is the temperature sensitivity, we get very different answers. And this is just because of these confounding factors of seasonal changes. In 2010, actually, we tried to address that with a relatively complicated frequency separation, saying basically, well, the temperature sensitivity acts on several timescales, in particular on the short timescale, so it's an immediate effect, while the overall activity rather changes seasonally at low frequency. So we get time varying coefficients of this RB, and that's how we can, at the end, separate the 2 effects and get more realistic and intrinsic non-confounded Q10s. But the idea here with a hybrid modeling is actually that we can model this variation of RB that is very biological and not so easily physically described to be described with a neural network. So we get the RB here from a neural network. The temperature goes into this equation, into this physical equation. We also estimate this parameter Q10 at the same time and optimize it all against the respiration. And this way we get both the RB and the Q10, the temperature sensitivity. And what we get is actually that the base respiration varies very similar seasonally as in the original study, with now with a hybrid modeling approach. So we can infer this RB, but we actually get additional variation. So this is not just a plotting error or noise. If we zoom into that, we do get actually variation of this RB parameter even at the diurnal scale. So that's something that we can additionally infer, because we didn't have to make any assumptions here on which frequencies the different parameters vary. Can't go into detail on the interpretation, but it's interesting that one can infer these kind of latent hidden variables with that approach. And the last one quickly is a little bit more complex and globally more relevant. It's about a hybrid global hydrological model with the same principle. We basically have a deep learning architecture that is feeding into a hydrological simple mass balance model. Maybe in the interest of time, I just leave it like that, but maybe just quickly here, for example, groundwater is a state that is updated with some base flow that is subtracted, with some recharge that is added, and then some other overflow that is also added to the groundwater to update the state. So it's really a kind of differential equation model, but where the coefficients, how things are partitioned and so on, how evapotranspiration is happening and so on, is basically learned or is modeled with a machine learning approach like with STM some other approaches. And bring that together brings actually quite good performance, and it can be learned in multitask fashion where several variables can be learned: snow, evapotranspiration, runoff, terrestrial water storage. And this way we can then diagnose water cycle components at the same time with this very data-driven approach, but physically consistent approach. We can see here how the terrestrial water storage is moving around during the seasons, or here on the upper right, accumulation of snow. And that is all now modeled with this hybrid model, which gives the advantage compared to other models that is really data informed. Let me skip that, which is relatively similar. Only the last thing what I want to say is that one can then also check what kind of patterns does the model retrieve. And we were pretty excited to see what the model does, for example, with a prediction of what is the evaporative fraction. So how much energy is used to evaporate water. And we see, yeah, it is actually going down. The evaporative fraction is going down when the soil water deficit is increasing. That makes sense, because if it's drier, then there's no water to evaporate anymore. But we see it's not always the case. At some point, actually, there's still very high evaporative fraction, although the soil water deficit is very high. And then we looked at it, and we color-coded here the time since precipitation more than 5 millimeters. And this is exactly the situation when you can have evapotranspiration despite soil water deficit, because the surface is wet. And we didn't tell the system at all. We don't have several layers in the system. It basically learns this intrinsically as part of the state in the LSTM, which is, I think, quite promising, that one can extract basically these latent variables and states from such a data-driven or hybrid system. Yeah, so just quickly, I just want to, maybe it's also moving towards Michael's talk, but I think one thing that we have been only starting to address, but I think it's important and exciting, challenging to also understand not only natural behavior of ecosystems, but also societal behavior and the vulnerabilities against climate change with artificial intelligence. One can have similar conceptual models as for the Earth system, where extreme events relate to health and well-being, social cohesion and individual well-being belong together, and both of them that strengthen resilience, which is also then affected by extreme events. But it's of course even more difficult to model that in a mechanistic way or physical way. And just one example, just a study that has been coming out, but by looking at hazard impacts across different domains, we see very contrasting impacts of weather extremes on biophysical and economical societal domains, here with mortality, property damage, but also attention. And here on the lower right, you see actually that particularly the attention for floods and storms is much higher in relative terms than the impact, while heat waves, frost, and drought actually get less attention, although the impact is actually quite high. I think that's, for example, one way one can look at these aspects, just with an empirical evidence and data-driven way. So my last slide is really a wrap up. I really want to emphasize, of course, that the data-driven science should not replace hypothesis-driven and mechanistic science, but really complement it. The classical way is really to start from the hypothesis, build theory, implement it into a model. We get predicted patterns that are then, ideally, we have then design new observations to confront and test the model. But we can also start the other way around, as I showed here in this talk. We start from the observations. We generate observational-driven products. We get observed and recognized patterns that can be used to generate hypotheses that explain these patterns. And then these hypotheses can be put into models, into new theory. And it's really getting, I think, interesting in this model data integration space, where then one can say, if observed patterns disagree with predicted patterns, then we have actually a surprise, and then we have an interesting puzzle to solve, which then helps advancing actually the science and also solve actually problems. So this is kind of this data-driven versus hypothesis-driven thing that we have always to consider. And last but not least, just a short advertisement for our program in the ALICE network, European Lab for Learning Intelligent Systems, Machine Learning for Earth and Climate Science. If you want to contribute to that, please feel free. You see here some of our goals that align very much also with this series. Thank you.
Fantastic. Thank you, Marcus. Thank you, Marcus. This was a really great talk, really comprehensive. And as you already hinted at, it might glue up nicely with Michael's talk. So as always, we take the questions in the end. There's already lots of questions in the Q&A, and feel free to add more questions to that. But for now, we move straight to Michael Obersteiner's talk. So to introduce Michael, he has a background in global terrestrial ecosystems and economics. He did graduate studies in Austria, and then both and also abroad at Columbia University and also at the Russian Academy of Science in Novosibirsk. And he really sort of works across many different components of the Earth system, from biophysical modeling in ecosystems, forestry, agriculture, all the way to economics, finance, and impact assessment. He then was working at the EASA in Austria and recently joined the Environmental Change Institute in Oxford as a director. Michael, we're very happy to have you here, and I hand over straight to you.
Yes, thank you very much, and I'm very happy to talk at this event. And I can actually seamlessly continue where Marcus ended. And I will talk about a concept which in economics is well established, even got the Nobel Prize, and this is value of information. And I will tie it into some work where we usually use machine learning, but also other approaches. But let me start a little bit more from a helicopter point of view, where just to remind you, when you look at the big picture in terms of socioeconomic development and the environmental crisis, we had the Millennium Development Goals, which you see on the left, where you look at the number of extreme poor people, which actually came down quite a lot, and many other socioeconomic indicators point to the fact that human development is actually on a positive path. By far not enough. However, really on the Earth system, we are really challenged, and I don't have to tell you that when you look at climate change and biodiversity only. It's quite an issue. When we now talk about, how do we achieve the SDGs, the Sustainable Development Goals, my basic hypothesis is that what we will have to do is more and more engage in something what I call algorithmic policy making. So exactly this kind of data-driven way, very much along the lines what Marcus was showing on the Earth system modeling, but also doing this in the realms of the socioeconomic domain. And especially when you have a background in economics, where there is a lot of theory, but also a lot of ideology, using machine learning helps you to unpack quite a few myths, and also you encounter quite a few interesting puzzles we need to solve. But what we practically need to do is we need to transform as it's pictured here, the energy system, the food systems, the city systems, and so forth, and use political but also economic instruments in order to transform this. And in order to do this, we need to have good enough data and good enough models to actually come up with robust policy portfolios that enable an socioeconomic transition that solves socioeconomic problems, but also solves the planetary environmental problems. Before I go into the modeling domain, I just want to remind you on, and this has to do a little bit with value of information, that many of those systems, even socioeconomic systems, are actually quite slow, and decisions you make have a long memory. And just to illustrate this is a land use map of the Austrian-Hungarian Empire somewhere in Styria. And this is the satellite image of today. So what you see is many landscape elements actually stayed on for almost 200 years. And so if you make a mistake in these kind of land use decisions, for example, the mistake might actually stick for a long time. So when we do these kind of policy impact assessments, we always start with the quality of the data. And when I personally work a lot on land use issues, but also food security and so forth. And then you look at some of the very basic data items, and this is a disagreement map of the global croplands of the world. And when you look, for example, here, it's in the northern part of sub-Saharan Africa, actually in those areas where you have the severest droughts and calamities, you also have at the same time the largest amounts of uncertainty of land cover. So planning for better policies is actually in that case grounded on rather poor data. So how do we solve just purely the data problem before we even switch on the machine learning machines? And this is, of course, we use satellite images, and we have now a slew of new types of sentinel images, but also if you look at planets and others, high resolution images. But still what we need is good validation data on the ground. And here, what we do is quite a lot. We use crowdsourcing to actually get human eyes still to look at what they think they see on the ground. To do that, we can even engage in games which people play on the bus stop. So, for example, here we have this cropland capture game which we designed, and these images and the validations are then used by machine learning algorithm and the community using these tools in order to improve these maps. And then, of course, what you see here is one of these hybrid maps where you use the crowdsourcing information, some other high-resolution images, and some of the latest image processing capabilities, and then you come up with the best product. But a simple thing like a global cropland map enters then into many other models that help you to plan for other natural resources. And one thing we just recently finished was an asset ranking for biodiversity, water, and carbon, which you see here. And then you have all of these underlying land cover maps with their uncertainties that help you to come up with such priority ranking of natural assets. This is just an illustration of all of the use cases that depend on better Earth observation and better machine learning algorithms, or even statistical approaches, to just generate something simple like land cover and land use maps. But then you can go even into more detail and look at the attributes of a satellite image, where we also use quite a lot of different machine learning algorithms, where you go into more segmentation problems, something like a map of field size, because field size gives you then a good proxy of the intensity of how agriculture is actually done. You know, if the field size is larger, you can assume that most of it is mechanized. You use tractors, agricultural inputs, fertilizers, and so forth. And if you have smaller field size, you can even infer back onto poverty issues and so forth. And that's also something we used in Senegal, where we did a huge data fusion kind of exercise, just to leverage some of the field size data, which I showed you before, but also combine it with night lights, telephone data, household surveys. But also interestingly, we looked at algorithms that classified rooftops, where the rooftop gives you a good proxy of where the wealthy are and where the poor are. And then you can come up with products that I show you here. This is actually was then poached by a marketing company, and they use this now for marketing targeting. So not always it's good to publish everything in complete open source. But now let me quickly dive into something what I really want to show to you, and this is this value of information and how you calculate the value of information. And what I take here is improved data or improved predictions from climate models. And this is about building climate resilience through adaptation measures in agriculture. So basically, typically what you start from is we have the perturbation in terms of increased CO2 concentrations, the climate changes, you put this into a crop growth model. Currently, by the way, we are using both biophysically based crop growth models, but also machine learning and the combination of the two. And then we look at how can we serve markets. And in order to do that, we currently use both linear optimization models, but more and more reinforcement algorithms from machine learning to actually come up with welfare optimizing models to simulate the economy. But coming back now to our experiment. So what we did is we stuck climate change signals from the different climate models into a biophysical crop growth model, and estimated that for Latin America, we take the example here, Latin America, and we observed that on average we have about 7% of yield decreases from climate change compared to no climate change. However, if you look at adaptation, climate adaptation, then you can change your crop management. And one type of crop management is irrigation. So if you expect more droughts to come, you build irrigation infrastructure, and you can counter some of that impact. So you actually have, through this adaptation measure, a positive impact, counterbalancing the biophysical impact you would expect from climate change. What you can also do is you can allocate your crops from an area which is where the crop is more vulnerable to an area due to climate change where it actually grows better. So that's another way to adapt to climate change. So here, for example, you see that overall in Latin America, it becomes a spot where you grow more soy but less corn compared to global levels. So corn travels to some other continent. And then, so what we observed then is what we call the final intensive effect. So here, the original biophysical effect from climate change of 7% is reduced down to something like 2.5% only. But then what's also interesting is you see that in Latin America, overall, Latin America benefits or is less impacted by climate change than other global areas. So overall, the supply in the end of Latin America increases in a world of climate change. So here, looking into climate adaptation and its possible effects, this is actually a quite complicated cascade of causal change. But now, if you stick in uncertainty into all of this, what you can face is you can face a situation where climate change scenario number one is predicted, and it really happens. Then you have perfect adaptation. If, however, you plan for climate change, the climate change scenario number two, let's say it's the dry one, however, it becomes more rainy, then you're in a situation of maladaptation. So when we calculated now all of these different scenarios and scenario combinations, what we observe is that the expected losses due to climate change are about $246 billion per year in the case if you don't adapt. So you just stick to your current patterns of cropping. However, if you perfectly know that that the dry scenario is actually becoming true, then this reduces by a factor of 5 to something like 43 billion. However, and this is really the interesting result, is doing nothing, so basically no adaptation, is actually superior to a situation where you maladapt, in the sense that you plan for a dry climate, you put in a lot of irrigation and do many other things. However, then it becomes more rainy, then you not only suffer from reduction in yields and economic income from climate change as such, but also from your lost investment, in this case irrigation, due to your wrong decision making. So here, the value of information is incredibly large. It's actually larger than the entire signal, whether you adapt or you don't adapt. So that's really an interesting situation. And we did many other case studies ranging from cases of forest fire management planning to landslides assessments. You always see that the value of information, so investing in better data and better algorithms and models is orders of magnitude more valuable than actually the production of these new data sets through investments of, let's say, in situ campaigns or new satellites and so forth. With this note, that the value of information is always much, much larger than the cost of producing it, I would like to hand back, and I'm happy to engage in discussions at the end of this session. Over.
Fantastic. Thank you very much, Michael. That was great and nicely followed up straight on Marco's presentation. So back to you, Duncan, will lead the discussion.
Absolutely. Thank you very much, both. It was a fascinating discussion. I wanted to briefly start with a question for Marcus. Thanks for going through the Q&A and answering some already. I know you mentioned the works that you've been doing with Jakob, and as you say, we had a really nice talk from Jakob and Emil last week on causal modeling. I wonder if you could talk a little bit more about how you intend to, or perhaps already have started encoding causal relationships and these causal diagrams in your modeling efforts, and whether, for example, the example you showed with predicting land changes under different scenarios, obviously there are correlations there that aren't necessarily causal, and I wonder if you might expand on that a little bit.
Yes, no, that's definitely a very good point. And also, on the one hand, let's say, I would argue that the hybrid modeling approach does already, of course, incorporates some causal thinking, because basically the mechanistic part or the physical part is, you have equations and you say which variable influences the other, and only those things where you are uncertain, you what the functional relationship actually is then modeled with a machine learning approach. So that, I think, that's incorporates causal modeling. But of course, then we have also other situations where we don't actually fully understand what is cause and what is effect if we have feedback systems, and then I think that's where causal modeling and also causal discovery plays an important role. For example, if you think about the hydrological cycles, for example, there's quite some discussion and open question if actually soil moisture is important for vegetation productivity or the air humidity, and soil moisture is also influencing the air humidity through regional feedback, so that the air, if the soil is dry, then the air will not be humidified by evapotranspiration, and that causes dry air, and this then increases vapor pressure deficit and causes stress also from that side. And some studies that actually a colleague of us has done together with us with a mechanistic model has shown that actually the indirect effect of soil moisture is very important. And now the question is, can we also detect that from observation? So that's, I think that's where this causal analysis is really important.
But where, in that case, you posit the causal relationship. You say this is the model that we've developed from greenhouse experiments or so, where you control all the variables, and then you use that applied.
Well, yeah. No, and that study basically it's based on the model, and then you can do a factorial experiment and you can get the causes. But my point was actually that, can we see that? Can we also derive that from observations?
Right. Okay.
Only from observations, and
which is much harder, of course.
Yes, which is much harder, but which is with the causal theory, and I think we won't go into detail. I think Jakob has shown these nice things, but with instrumental variables and these kind of things where one can avoid confounders, one can get there, and this is an exciting field of research, I would say.
Yeah, absolutely. I wonder, actually, I had a linked question for Mikhail, and it's fascinating watching your talk, because I rarely consider the kind of societal aspects of, or side of the problem in the physical research that I do. But how do you deal with societal feedbacks in disentangling these kind of cause-effect questions? So obviously, we might choose to adapt in a certain way, but that may modify our behavior and change the scenario we end up in, potentially. How do you consider that in your models? Do you have like societal feedbacks that changes in behavior or changes in?
Yes. So one issue which is quite well established in economics is called the rebound effect. Mm-hmm. So for example, if you have more efficient light bulbs and you save money, and you might actually save greenhouse gases, you might end up using more of them right. In the end. And you have similar behavior with eating behavior and other things. So there are these kind of rebound effects. However, we have a similar problem in economics, and probably even a larger problem, because with many things we cannot do any experiments, because you cannot experiment with an economy. Is actually causality, and there are statistical approaches, and there was even a Nobel Prize given out again on causality testing in economics. So that's quite an established field. However, on the practical side, you conduct these causality tests, which are statistical approaches, and many times I would say they actually fail, and you need to look for other avenues to attack it. So this is really interesting. And I think this is also consistent with what Markus was telling before. With these new data-driven approaches, we can all in a sudden do stuff we couldn't do before. So in economics, when I studied economics, it was a science of aggregate variables. Now it becomes a science with tons of information, agent-based modeling and so forth, right. Which is really revolutionizing the type of science, but also raises tons of new ideas, and you can do very different things, just as you do in the physical sciences.
Yeah. Oh, that's exciting. Thank you.
There was a question to Michael that was quite similar to one I posed myself, and that is the uncertainty, how to deal with uncertainty. And the question is from Robert Bernard, when you're doing any of these modeling estimate costs, you give very precise numbers like 43 billion, but aren't the data and models you're using quite uncertain? So should one not deal with this in a stochastic or probabilistic sense rather than in a deterministic way? And I wonder, particularly then also bringing in AI, what do you think about methods and ideas to deal with these uncertainties, how to propagate these through the whole sort of system all the way to the costs in the end?
Mm-hmm. Mm-hmm. Very quickly. So I remember still one workshop I participated in where it was basically about air pollution policy. And the question was, shall the policy process deal with uncertainty or not? And at the end, the conclusion was, no, we don't want this because this complicates decision making for many reasons. One is policymakers typically don't understand uncertainties. And even if they understand it, for them, it's a terrible way to communicate what they do. Because we have seen it now in the COVID pandemic. No one comes across as someone who actually can lead the country, and that's what political leaders want to do, simply because it's more complicated. So there's overall resistance out of these more, I would say, psychological issues. The other thing is there's, especially in finance, there's a good tradition of stochastic optimization. So for example, banks do stochastic optimization, and there's even stress testing, formal stress testing, whether in stochastic environments banks can actually survive, and if they don't keep their money in a certain way, they actually face quite a lot of regulatory pressure. So there is a lot of tradition, mostly in finance, not in economics, on stochastic optimization and characterizing the uncertainties. And then there is a more principal problem in economics, is that uncertainties you typically you only want to observe from the past. Forward-looking uncertainties is a huge problem, especially when it comes to regulation. So for example, if I were to get money for an irrigation project, and I would stick in forward-looking climate change scenarios, a bank would not accept that. Also because the regulation is such that this information cannot be taken. And however, this is something we really need to work on together, that this becomes possible, that we actually learn from the future and work with future-oriented information, however, take the uncertainties serious and put it into the decision-making context. I stop here, but there are many, many more things to discuss about this.
I mean, I guess a key difficulty is propagating uncertainties as well. I mean, we've discussed in some of the talks in this series the difficulties and uncertainties in modeling the physical climate, and so even dealing with those uncertainties is difficult enough without then propagating that through to other aspects.
Yeah. And if the uncertainties are large enough, then many times the best strategy is actually to wait. So out of the experiment I was presenting to you, the best strategy is to just carry on with do nothing, and then wait till you have a strong enough signal, a clear enough signal that you can commit towards, let's say, investing into an irrigation infrastructure or not. And it's sometimes you don't want this.
No, I was going to say that's
behavior.
Interesting. Okay, thank you.
Great. I have a follow-up question from a question that you already answered, Marcus, and that is, so the physical climate system or versus human dimension, and so in many of these land use modeling scenarios and land use models, including AI, quite often we assume the humans aren't there, and in many areas the human change will dominate. So is AI and coupling these different AI models, is it a way to address some of this? I mean, because it's in most CMIP model scenarios, so the coupled climate model scenarios, this is really separate. You have a fixed scenario and stick to it. Is it a new way of advancing this area, or is it still in the infancy?
I would rather say it's in the infancy. I think that's one of the hardest problems, and that's probably more actually a question to Michael, because I mean, modeling this human decisions, human behavior based on factors like how the physical environment is, but also based on what is the political context and so on is very, very difficult. And so, but I think one can use AI again together with the big data and information about, for example, time series of land use change that we have now gathered in Latin America and in Europe and in US and so on, and which is also aided by Earth observation in this objective way. By looking at that, one can possibly derive context-specific rules that people actually take. But I think that's really an open question if one can generalize it or not, or how context-specific that needs to be. But I think we will certainly learn something by analyzing these data and looking at these questions. I'm pretty sure.
Mm-hmm.
Great.
Yeah.
Maybe one little comment from my side. So one other additional strategy which we are working on at the moment is that we actually play games and let decision makers play games and use AI algorithms to infer on some of their behavioral parameters. And this you can use then further to do predictions.
It's interesting. That would
seem politicians to a training data set.
Yeah.
But maybe one point that I would like to make, also there were some other questions about how one can show that the predictions with AI are better. I think predicting is, of course, one important task, and in particular, if it's more short-term and not so much extrapolated, either in variable space or in time space, and then it's also very plausible that one can make good predictions. But my point also partly was that it should help, AI should also help in understanding the system better and then inform models or hypotheses, learn something about some hidden variables that we couldn't observe, and then improve the understanding, which then can lead to better models that do better predictions. Because I try to make that point quite clear, particularly if we use just some machine learning approach, a black box approach. This is nothing else than a statistical model, and it will not be able to extrapolate beyond the domain where it has been trained on. It can extrapolate a bit, but the further you go, the more unlikely it will be. So that rule, I think, will never be broken. So we need this hybrid approach.
I've just seen Michael has answered the question I was going to ask, but I'll ask it anyway. So I think he's your predecessor, actually, Michael, right? So Professor Jim Hall here in Oxford. So he's surprised by the dramatic shift in value that you get through maladaptation, and asks if that only comes about if you really get the direction of climate change wrong, and whether actually just getting the magnitude of changes, for example, in temperature or precipitation, might not have quite such dramatic effects. But maybe you can expand on that.
Yeah. Well, in this case, it was really crop yields in these models, at least on the global level, is quite heavily driven by the precipitation uncertainty. And right. There you have problems even whether you get it directionally right,
Yeah.
because you can go dry or wet, and so here you have this enormous value of information and these decision dilemmas where you in the end you want to wait till you get more, actually even on the directional side, confirmation. So this is a little bit of an extreme case, and there are other cases where it's clearer and you can commit earlier, and you know what to do.
No, but certainly regionally, I mean, models rarely agree on, like you say, the sign of precipitation changes in a given location, and some of those locations are critical, in the Sahel and regions like that. So
yeah,
that's interesting. Maybe more. Sorry, go on, Philip.
I was about to make a slightly cynical comment. Critical is unfortunately, if you express it in value, then it's unfortunately the Sahel never comes up high enough because the human value doesn't count as much as the dollar value. That was maybe a bit cynical. I mean, I wonder if we should ask the last question that is in the chat to both of you, because I think it's a really good one. And that's a question from someone, I can't pronounce the name possibly right. So it's Nabuyama Jean de Dieu from Rwanda, and asking, in which ways can we empower our children with skills for future climate change solutions? And I think it's a really good and timely question. And I wondered if both of you had some thoughts on that.
Markus, you go first.
Oh, that's a very, very important question, because I think all the science doesn't help if it isn't used and isn't used broadly. So of course this is a lot about capacity building, but from the start. So not only scientific capacity building, but also making data and results available and useful. And I think that's actually where UN bodies come also into play, and where one needs to design, and that's already happening. Like apps that convey the information, open data, open knowledge that can be used by local farmers, for example. What's going to happen in the next 2 weeks, and I believe almost that it's important, that it's probably more important that the communication of the results is done in a way that they are practically useful, instead of that everyone needs to be trained in an academic way and empowered to be able to understand all the science behind it. So it's really more on that side. I think we need to make sure that these results that we have become more practically digestible. Like driving a car. We drive a car, we don't really understand how, well, it depends on you don't need to understand how a car functions, and you can still drive it. And I think that's how we also have to deal with information on the earth at the end.
Mm-hmm.
Can I just chip in there? I mean, that puts an onus on the information producers to produce relevant and pertinent information. In particular, I think sometimes we're guilty in climate focusing on, as Philip mentioned, Europe and the developed world in terms of impacts. And I think maybe, if we are to make that impactful information available, we should consider where we look and who.
So just for example, I mean, the example of this landscape prediction, how landscape responds to drought. We are just right now in a project, DeepCube, that's an EU project, but where we work together very closely with African partners and the Office for Humanitarian Action, as well as the Center for Monitoring Displacement, Internal Displacement. And then I think it's really important to discuss with the humanitarians, for example, what kind of information is actually needed to do a good early warning. And we have been in December, we had very good discussions where we learned a lot what's actually needed at different time scales, lead times, and so on. So that is really important. We need to engage with the relevant people.
Thanks.
Mm-hmm. So this gave me a little time to reflect a little bit. So, so thank you, Marcus, for going earlier. I think it's really the most important thing we see, and there's lots of even scientific evidence. It's really education. And education is the best investment, but not only in terms of, you make yourself economically better off, and therefore you are typically more resilient to climate change, but you also make smarter decisions. And also you make more responsible decisions. So there is evidence that people with higher education, that they consume actually, if you adjust for their income, of course, consume more responsibly than others do. And then the hope would be that your child actually gets a science degree and actually becomes an information producer.
It's a very good point. And I was about just to add to this exactly in the theme of the series about AI for good and AI for climate science. People often ask, what should you study to do climate science? And here, particularly also AI, and particularly for kids and at school, something quantitative, getting excited about, not too scared about maths is a very helpful thing. And that can lead them into these fields. And then if one becomes a climate scientist, that's fantastic. And on the side, one can still become a data scientist in a very well-paid position and support climate science this way.
Brilliant. Well, I think that's a good point to wrap up this week's session. So thank you both very much for your time and for the interesting talks and discussions. It's been a great talk. I think we are going to, we'll have a wrap up shortly from the ITU team, but I'll just briefly introduce next week's talk, which isn't next week, it's actually 2 weeks today, on February the, help me someone, 16th, is it? Yeah, 16th of February, so 2 weeks today. And we're going to have Gustav Kampsvalls, who I think worked with Marcus before and was mentioned in some of those slides, and Manal Maski from NASA, who are going to describe some of the uses of AI and machine learning, particularly with a focus on Earth observing data, so satellite data. So we're very much looking forward to that. But we'll close there, and thank you very much again for the discussions.
Thanks very much, Marcus, Michael, Duncan, and Philip, for a very interesting discussion, and also to the audience. There are a lot of great questions in there and engagement. We are now opening a quick poll with one question. Please answer and let us know how much you liked this session. As well, just to let you know, you can rewatch this session at any time on our AI for Good YouTube channel and share with your friends and colleagues. We also encourage you to check out the AI for Good program online at aiforgood.itu.int to see more sessions, including with the climate science series that may be of interest to you. And lastly, we'd like to once again thank everybody involved, the panelists, our participants, partners, sponsors, and co-convener Switzerland. We hope to see you again soon.
Selector, rewind selector, rewind selector. Rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector. Rewind selector, rewind selector.